tested in the lab. So another thing maybe you want to ask is like, well, you have a seed, I want something to have higher affinity. And then you just get a sequence that you can also ask for. Maybe you even want to do something more complicated, like de novo design, where you don't have a seed at all, you just have a target, and you just want to create something that binds to the target. And you can just also chat with that bot. So if we want to do that, what do we need to have? So one thing we need to do is we need to have that chatbot understand English. So it needs to understand tasks like, well, if I'm giving it a protein, I want to decrease hydrophobicity, and I gave it a constraint of smaller than 5 edits. So it needs to be able to understand that. The second thing we need it to do, it needs to be able to understand proteins, and it needs to be able to understand the different concepts in proteins and how to change them and reliably control them and generate something that is reasonable based on these particular concepts inside the protein. So luckily for us, the first part, we kind of like AI has figured it out. There's a lot of language models that seem to be understanding English pretty well. For the second part, we did like some progress. So there are models like Lobster and ESM that understand protein representations. But unfortunately, just protein representations are not enough to perform these particular tasks. We need models that understand the different concepts inside the protein that make them what they are and knows how to edit them and change them reliably. And currently, there aren't really anything that can do that reliably, or we are kind of confident enough that it actually understands the underlying properties of proteins. Okay, so let's talk about masked language models first. So masked language models were introduced in 2018, first in the Burke paper. And the idea was, well, as English, how did we get tested in English at school or language at school? Well, we got tested by complete the sentence. In the exam, they used to give us like dotted lines and ask us to complete the sentence. So people thought, well, why don't we train a transformer that can on this task, which is complete the sentence task? So that's what basically a mass language model is. We have a sentence, we mask some tokens, and then we ask the model to predict these tokens through cross-entropy loss. And it seemed to do pretty well for English. So people thought, well, let's do the same thing for proteins. So we have a protein sequence, we mask amino acids, and then we ask the model to predict that. And that kind of went on pretty well, and we were able to learn protein representations from it. So people thought, okay, so now that we are able to learn representations, how can we control for these representations? So one idea was let's create conditional mask language models. And what does this mean? It means that we want the output to have one particular condition. And one very simple way to do that is to add the condition as a tag in the sequence itself. So this is an English example where it says, okay, we want to produce an output that has the concept female. We'll just give that as an input, and the model can kind of use it to produce something that has a female. And hopefully, when it sees an example where there is female and woman, it learns to relate female with the word woman. So every time we ask female, it gives us the word woman. So people thought, okay, we can do something very similar for proteins. So if I want something to generate a bacteria sequence, we'll just give that as a tag. And hopefully the model will learn the correlation between the bacteria and the output. And every time I give it a bacteria sequence, it will be able to produce that. So there are some problems with this type of models. The encoder, we don't know what it really learned at all. So it's a black box. We don't know what it learned. The second thing is we don't know how the decoder is making decisions. Like, why did it produce amino acid E and not A? We don't know how to answer that question. Also, we don't know what this model can and cannot do. What did it learn and did not learn? What task will it fail? we're not aware of that. And finally, we aren't able to debug or fix these models by any means because basically it's completely a black box. So the best thing we could do if it's not working is fine tuning data, try to retrain it, or basically throw it and build it from scratch again. So um, we're going to be in our work, we're trying to fix these problems for like by our concept bottleneck model. So let's talk about again conditional generation. So so we can give the conditions as tags as done here, but the problem with that is that the model can completely ignore this in the learning process. So there is no really incentive for the model to learn that this is a bacteria. One way people have adapted this is like, okay, give it a condition as a tag, but also make it predict that condition. So tell me, and this is like conditional VAE or like any simple conditional model where you just give it the condition and ask it as a tag. But one can imagine that there can be like a residual connection between the input and the output where it is just trying to pull that information forward and not using it to learn anything reasonable about the protein.
And I fenced for APA. I started fencing when I was 7 years old.
Um, so yes, so that can be one problem. So one other solution is, well, you can say, well, maybe if we wanted to learn that it's a protein, we don't always give it the tag. Sometimes we mask it, sometimes we give it the tag, and then it will kind of have to learn that the sequence is, sorry, bacteria. So in this case, well, maybe yes, it does learn that the sequence is a bacteria, but we don't know how these tags affect the model output. So is it using the information that the sequence is a bacteria to actually produce the correct output? Is it learning the biophysical properties of the protein? All of these different things are really unclear in this particular model. So we try to fix this by our model, which is we call the concept bottleneck mask language model. So basically, all the problems that we had with the conditional mask language model, we'll try to kind of address it here and fix them one step at a time. So first, the first problem we had was that we don't know if the model learned the things that we cared about. So one way we could do this is we added something called the concept bottleneck module. And this particular, I'll go to details about this module later, but what it does is that it predicts the concepts that we care about from the sequence itself. So this module basically, let's say that we care about species, so it predicts the species of the model from the sequence. And we have a loss on that, so we know that like, okay, was it able to predict it or not? So this is the first thing we added. The second thing we said, okay, we have this new network. We called it an orthogonality network, which is basically now that we predicted all the concepts that we cared about, we want something to separate the concepts that we cared about that we predicted and everything else that is in the protein that we didn't encode. So this particular model, what it does is that it basically answers us, it gives us a new token, a new embedding that does not have the concept information that we already extracted. So what we do is we take the concept information that we learned, we take the things, the output of the orthogonality network, which we call the unknown, because we basically don't know the concepts in them, and we put them back. So the blue embeddings at the token level, blue embeddings are kind of equivalent to what we have here, but here we kind of try to separate them so that we have concepts and unknown concepts. And then based on that, we are able to use that for making the final prediction. So on top of that, we added a linear layer that is basically able to take the known and the unknown concepts and project that to produce the final layer. And since this is a linear layer, we can kind of see that which concept it depends on and how are these concepts used to make the final prediction. So just to recap, um, the concept bottleneck module, make sure that we learn the things that we care about. The linear layer, basically, we can look at the activations and the weights of the different concepts to know what the model used to make a certain prediction. And then we have the weights. If the weight is set to, if the weight of this of a certain concept is set to 0, it means that the model was unable to learn that particular concept. And then if we want to see if we can use this architecture for debugging by simply looking at the concept loss to say if we aren't able to learn a concept, then the loss should be 0. If we're able to learn the concept, then the loss would then basically, if we're able to learn the concept, the loss will go down to 0. If we're unable to learn the concept, it will have high loss. If we look at the weights and the weights are 0, it means that we were not able to basically use these to learn weights for this particular concept. If the weights are reasonable, then we are able to learn weights for that particular concept. And that means we'll probably be able to control for it in the future. So this is kind of like what we thought we could do to make basically the complete black box architecture to have like the different properties that we want. Okay, so I'm going to go into like different details about the like how we train this model and the different submodules. But like this is a good point to have like questions. So if anybody has any questions, I can take them. If not, I can just continue. Okay, let me continue then. Okay, so I see somebody posted something.
Yeah, we have a question in the chat box.
Can you read it? For some reason, I can't access.
Yeah, yeah. Kevin asked, are concepts defined before training or learned during training? I guess it's a label given, right?
Yes, it's a label given, so it's defined before training. We have a set of defined concepts, and like the unknown part of the embedding has like everything that we did not define. Okay. Cool. Let's go into dive into the architecture. So this is kind of what we have. So the first thing is like do we train it? We have the regular mass language model loss, which is just the cross entropy loss between the token that the model predicted and the actual output. And so this is like your regular just traditional mass language models. So that's that. The second thing is this concept module. So what does this concept module look like? Well, we take the token of the CLS token. So the CLS token after the encoder would have information about all of the other tokens. So any concept that is in the protein should be in the CLS token at that point after we're done with the transformer encoder. And then we put, it's like you can think about it as a multitask network on top of that that predicts the different concepts. So if you have like a different number of concepts, so it will predict a value for the different concepts. And then for every concept, we have basically an embedding for that concept that we multiply the concept value with that embedding value to get the final concept embedding. So the concept embedding is the concept value multiplied by the embedding. So this concept embedding is basically a learned embedding, similar to the way you would learn tokens embedding, but these are concept embedding in the sense. So now you have a concept value, concept embedding, multiply that, you get a vector that represents the concept in the protein itself. I'm sorry, 1 second, they're kicking me out. Yes. I apologize. There was a
Okay.
problem in the meeting group.
That's okay.
Okay.
Thank you.
Okay, so yes, so basically, yes, so we said that we take the CLS token, we extract labels for the different concepts, and then we have embeddings that represent the different concepts. Now we multiply that, the concept label with the concept embedding to get the concept representation. And this we call the known embedding. So then, so basically the loss here, it's just loss. So if we're doing binary here, this is mean square error because we're doing continuous concepts. If you have binary concepts, you just use binary cross entropy, multi-class, you would use cross entropy. So yeah, that's the main idea of the concept module. And then you can use this to track if there is if the concept loss is going down, it means that the model is learning that concept. Okay. The last loss we introduce is called an orthogonality loss. And the idea of this loss is, well, we want this, we kind of want to disentangle the known and unknown parts. Well, disentanglement in general is a very hard problem. So we try to kind of force them to encode different information. And the way we do that is that we have a new network that takes the token and it produces new embeddings. And we try to minimize the design similarity between the known embeddings that came out of from our concept bottleneck module and from the like orthogonality network. So by minimizing the cosine similarity, we're hoping that they can encode different information. So yeah, so this is the final loss we have. So our total loss would look like this: your mask language model loss, your concept loss, and your orthogonality loss. And yeah, and that's basically it. So, okay, how do we intervene on this network and how do we get it to do kind of what we want it to do? So you can think about that like this is the mask language model at the end of the day, right? So the only thing is going to predict is whatever has a mask. So the question here is what do we mask? So if we mask something totally unrelated to the concept and then ask the model to, and even if we have like the best model in the world, we mask something wrong. So it's not going to do anything useful. So we need to make sure that this masking, we mask the things that are related to that particular concept. And yeah, so the first thing you could do is you can just randomly mask. But again, if you do that, well, you might be basically shooting yourself in the foot by masking something that's not related to the concept at all. So that's not good. The other thing you could do is something called occlusion. And what occlusion is that, well, you're going to take token by token and you're going to basically perturb it and see how the concept is affected. So after you do that, you're going to see which tokens affected the concept the most, and then mask them and produce the output. But imagine if we have a very, very long amino acid, long protein with so many tokens, then this would be very inefficient. And we're doing this on scale. So occlusion is really not ideal here. So we investigated different things, but what we found is the best thing you could do is for a particular concept, you get the gradients of the input and you compare that to a reference point, which here would be the mask because we already did masking. And you basically, the contribution of the different tokens is the gradient, the contribution, the difference between the input and the reference point, and you multiply that by the gradient. So basically, this tells you, well, how did this particular token contribute to that concept with respect to a certain reference point? And this is basically a single step integrated gradient. So that's kind of like how we do masking. So when you want to intervene, you basically find the concepts you want to intervene on, uh, and then you calculate the different tokens that you believe have the most effect on that particular concept, and then you mask these concepts, and then you intervene on them. So that's kind of like the high level idea of our whole architecture. Okay, so I'll jump into like the capabilities that our model offers and like show some results. But yeah, if anybody has any questions, this is also a good stopping point. Okay, let's talk about like what does this model offer for us? So when people think about language model, they always think about scale. And we introduced a few things here. We have like auxiliary losses. We added like constraints into the model. We put a bottleneck, which kind of like constrain the model a bit. So a question is, can we scale this? Because if we can't, then it's really not that useful in language model. So what we tried to do is we we looked into if we can scale it to different parameter size. So we trained a 24 million parameter model, 150, 650, and a 3 billion parameter model. We trained it on Unira 50 and Swissport, and we had different concepts. So overall, over 700 concepts, and these concepts were either Swissport labels or were BioPython concepts that we calculated per sequence. And what we found is that like we compared it to a few open source models and like a few baselines that we introduced. So for example, we compared it to Lobster is a mask language model. We compared to ESM2, which is also an unconditional mask language model. We compared it to a conditional model, which we called CB-pLM, and we compared it to a conditional classifier model, which tries to predict the concepts, to classify the concept at the end. So both the conditional model and the conditional classifier model would need the tags during inference, the rest don't. And we looked into the perplexity at different scales, and we can find that basically for different models, we almost match like state-of-the-art perplexity on a held out test set. So we tested on the Mason dataset, which was not in UNIREC at all. So yes, so that means that okay, it's good that we can scale and we get like good representations of the proteins itself. So that was the first thing we wanted to make sure of. The second thing we wanted to look into the different capabilities that this model offers. So I talked about control, interpretability, and debugging, and this is like I'm going to go over how we looked into the different things. But I think there was a few questions, so maybe I'll stop and take them first.
Yeah. The first question is, how do you encode the concept using the same transformer encoder uh, as a sequence? Right.
Um, so we basically try to learn the concepts through this. So this network is just learning the concepts. We have labels for them, and then we're just trying to learn the concepts from the labels during training. So that's kind of how we learn the concepts.
Oh, so the C1 hat is logic, right?
Yes.
Right. We have a second question here. Could you take a pre-trained encoder instead of training the encoder from scratch when you train the model?
So that's a really good question. We didn't try. I think we in like preliminary results we kind of tried to do that, but it didn't work as well. So we ended up training it end to end from scratch. Um, I guess we could have like investigated more, but like yeah, we did not like look into that. We trained everything from scratch end to end.
We have another question here. What kind of concept are you using? Functional or biophysical properties?
Both. So overall we had like 700, oh sorry. We had like 700 concepts, which were a combination of functional that come from Swissport. Like, for example, um, which species does this come from? What's the function of this protein, and so on. But also, like everything that was we can get from BioPython, which is like just molecular weight, hydrophobicity, gravy, aromaticity, and so on. So we had both concepts.
So you treat these like 700 concepts equally during the training, or you like adopt a hierarchical way to do it?
No, we treat them all here. We assumed like a hot like a hot encoding, which is not necessarily. So it's not so like an embedding that the concept is either is a, so Python concepts are real numbers. So it's either the concept is either there or not. So, for example, for Swift port concept, not all proteins were labeled, and also we used UNIREP, which does not have labels. So, if the concept is there, we basically backpropagate the loss from the concept. If not, we don't we assume that that label is not there, so there's no loss to be back propagated. And for real value, we used mean square error as the loss. For binary concept, we use like binary cross entropy for the loss. But all of the concepts are treated equally, but it depends on if that for that particular sequence, if we have labels for that concept or not, basically.
Okay, great, thank you.
Okay, cool. Okay, let's talk about the things that this model offers us. So it gives us control, which is similar to what you would get for a conditional model, but it gives us two more capabilities, which is like interpretability and debugging. So let's talk about control. So what does we mean by control? We mean that, well, we can basically go in and change a particular concept and then end up with a protein that has this particular property. So if we want to increase the helix, we start with one protein, we switch that concept up, and then we get something that has more helix fraction and so on. So how do we measure control for evaluation? Well, it's good that we used BioPython for for really quick in silico evaluation. So what we did is that we started with a set of proteins, we calculated property using BioPython, and then just for testing, what we do is that we intervene either by increasing a particular concept or decreasing it. And after that, we produce a new sequence, and then we measure that sequence again using Python and see if there was a change or not. So we look into accuracy. And here by accuracy, I mean that, okay, I increased gravy. I have the sequence before and after. Did actually gravy increase? And then we compared that with a regular conditional model, which is CB-pLM, a classifier one, which is the architecture that we showed at the beginning, where you have the concept as an input, but you also have a classifier head at the end to try to predict that. And then we compared it to our concept bottleneck model. And like we can see that like overall, this is the average accuracy over 14 concepts in both positive and negative directions, that the concept bottleneck model did a lot better and almost achieving like almost perfect accuracy. And here it's for the 24 million parameter model and the 150 million parameter model. But also more interestingly is that we noticed that the change that the concept bottleneck model gave us was a lot larger. So like if we say, okay, decrease gravy, then the decrease that our model offered in the new sequence was a lot larger than the other different sequences. So that was also here. We can look at like the average change was a lot higher for the concept bottleneck compared to and other things, which means that it kind of like it was able to optimize the tokens that were important. It was able to change them to the things that it thought more, and the result of that is better interventions and better control. Okay. One thing that we care about a lot in protein design is that we want to change a concept in a protein, but we want the protein to still be natural as possible. So we looked into how changing how the distribution shifts in a particular concept, along with how the naturalness of the protein is. And what basically for here, this is like positive intervention. So we would hope that basically the shift goes to the right, but the naturalness kind of remains the same. And this plot shows like the different models. The concept bottleneck model is the red one. So for the positive intervention, you can see it kind of goes to the right. Naturalness, of course, was a little bit affected, but not that much, which is good. similarly for the negative interventions, it would go to the left. Yes, so the dotted line here is like the reference point where the original protein, if nothing changed, it would be like that dotted line. So it seems to be doing the right thing, shifting the whole distribution of the test data set while preserving somewhat the naturalness, which is great. The other thing we looked into is like what happens if we try to do this iteratively. So we intervene on a concept and then we take a protein, the output of that, and then we intervene on it again. Does the property continue to increase or decrease? And we can see that that's the case. So here, this is like we intervened 3 times, and we can see that the property for the positive was increasing as the intervention increases, and the property for the negative intervention decreases as we keep on intervening. So that was really good to see. The other thing we looked into is, okay, a lot of time we don't really deal with one property. We're in a multi-property problem where we want to optimize 2 things at once. So how does that work and how do we perform in that? So here we looked into basically changing gravy and pH 7, charge of pH 7 at the same time. And we can see that like we can achieve like 94% accuracy in like both in this case. So random here would be around 25 because you're changing two concepts at the same time. And yeah, so that was really good. We could see that like we can, so here we were increasing both concepts, and the other one here we were like decreasing both concepts. So the optimal would be like this large quartile on the right, on the top right for the positive intervention as an example. So yeah, so basically our model works well in multi-property settings as well, which is great. Um, okay, so I'm going to talk about interpretability next, but I think there was a few questions, so maybe we can take them first.
Yeah, the first question is still about the concept. How do you combine the concept? For example, functional annotation alone is probably more than 700. And you also mentioned the species. Yeah.
So yeah, so basically so for the functional, we looked into the Swift port labels, which are which have the different functions. So we created like for these functional ones is like a hot encoding if this protein has this function or not. And then that's kind of how we trained. And for the species, we looked into if it's a bacteria or not. And also that's kind of how we made the training data set. So we used Swissport labels in that particular context to get these labels.
Okay. The next question is, how do you know which residue should we mask when we ask it to increase or decrease gradient?
Yeah, so was with the integrated gradients approach that we had, that basically where you look into the concept and then for that particular concept you find the gradient that for the different inputs, and then you take the change in the gradient between the token itself and the mask, which tells you the direction you should like which residues were most important for that particular concept, and then you mask these residues, and then you change the value of the concept in the concept bottleneck module itself.
Okay. There's another question. Orthogonal loss between the embeddings of the concept, so that you can better increase or decrease them independently from each other. Would that help in having even better control?
Um, that's a really good question. Orthogonal loss, we thought about like making every single concept orthogonal to each other, which might actually be even better. But it's just that we felt like it would complicate things a lot more. And since these concepts are already supervised, we felt that it's fine to not make them orthogonal and just make them orthogonal for the unknown part. Because it's going to slow down training at the end, because you're going to have to make every single output, every single concept embedding orthogonal to every other one. So we just chose not to do that just to make sure that it doesn't take a lot more training. So just to note, like this takes a little bit more than regular masked language model training in terms of like hours. So I think it was around 1.2, but which was acceptable because it gives us a lot more things than regular masked language model, but we didn't want to make it to be even slower than that. So we did not add orthogonal losses between the different concepts. But that might even improve control even more. But also our results on control look pretty well, so we didn't investigate that more.
Oh, great, thank you. Another question is, when you look at accuracy, you mentioned the concept are labeled as existing or non-existing. But how do you determine if the concept probably increase or decrease? Also, how you compare the outputted protein against data that are already existed in the training data.
So, okay, so everything we do is on a test data that was never, that we did not have in the training data. And with the concept that we looked for accuracy, and here we're Python concept that you can just calculate in silico from the sequence. So we give it a sequence, we calculate the value of gravy using Python, and then we intervene with whichever model we want, and then we have a new sequence that we calculate again. So here that we have like one input, one output. We don't compare like one input with the distributions. Like you have only yeah. So every input we have just one output, and that's what we compare it with. Um, so yeah, and since these are BioPython concepts that we look into here for the in silico results, it's really easy to kind of calculate that from the sequence. So that's how we did it.
Yeah, I guess the following two questions are quite similar. The first one is, have you compared your concept bottleneck PLMs to ones that use direct preference optimization by any chance? And the second one is, have you compared it with other optimization algorithm like bias optimization?
Yes, we did. So we had we did that with like an antibody, siltuzumab, I think, and then we compared. I think it was Lambo, Walkjump, and we found that we were able to kind of achieve similar performance to that. But these particular models, for example, uh, we're optimizing one concept. So you have to train the whole model to optimize a single concept. But here you can like you already it's a pre-trained language model at the end of the day, so it has a bunch of concepts that you can just change for. So we found that like we are in pair with like optimizing a single concept on training a single model to optimize a single concept, which was great.
Okay, great, thank you.
Okay. Okay, so back to interpretability. So we said that this concept bottleneck language model offers us interpretability, and basically, we have two types of interpretability that's offered here. First, it's called like local interpretability for a given sequence for like, why did the model produce a certain residual over another one? Like, why was the output amino acid A, not H, and as an example. And then this is really easy to answer over the sequence level by just looking at the logics of this particular of the concept bottleneck module. So in this case, well, we predicted this because we depended on these different concepts, and that's why we made that particular prediction. And this is on like the uh, sequence level. So the other things that it offers is more of global insights on the relationship of the model, of the concepts and the tokens. Like what did the model learn? And this is offered through the linear layer. Since we have a linear layer, we can kind of like just plot the weights. And this is an example of like what the weights look like for our model. So this is charge at pH 7 and charge at pH 6. And this is the weights learned by the model. So if we look into this, we can see that like the acidic amino acid have negative weights, which makes sense. And that's kind of like what happens in what we expect to happen. The basic amino acid have positive weights, which is great. And the difference between pH 6 and pH 7 is in histidine, which basically contributes towards positive charge in lower pH and negative charge in higher pH. So we can just look at these weights and how they contribute to the different amino acid and see for if we didn't know, we'll know figure out what the model is learning, and we can also validate that with human knowledge. So this makes sense that the model is doing the same thing. So this is kind of like the global insights that this particular model offers. That is not possible with like conditional models or other type of models. The second thing, the last thing that it offers is debugging. So what do we mean by model debugging? Well, first, it means like we can detect errors and we can try to fix errors during training or during testing. So basically, our concept bottleneck model, what it does is it allows us to kind of like answer these questions. Did the model learn the important concept that we're interested in? Is it relying on some spurious features that we don't understand? What situation is it likely to fail? And how is there a way that we can kind of like correct unwanted correlations in the model itself? And we can basically answer this by one of two things. First, we can look at the loss of the different concepts. If the model is learning a concept, then the loss should be going down. If it's not learning the concept, then the loss would be high, and then that concept was not learned. The second thing we can do is that we can look at the different weights of the linear model to see if if it has like reasonable weights for the different amino acids for that particular concept. If it doesn't, it means that it really did not learn that concept well. And we can also have the option to like change it. Like if it's learning a spurious correlation between some concept and amino acids, we can literally go in and change that to what we want it to be. And that will basically change how the output of the model behaves towards that particular concept. So as a test example, we wanted to show that this is actually the case. So we took aromaticity and we plotted what our good model, like the model we trained on, has the weights for aromaticity across the different amino acids. Then we took that concept and during training, we basically randomized the values. So the model was not able to learn the concept during training. But the perplexity of the model looked fine, so it means that the model was able to generate reasonable protein. It just did not learn aromaticity. And had we not known anything about the training process and we just look at the weights of these different models, we can tell, well, okay, the first one, it looks like it learned something, a relationship between that particular concepts and the outputs. The second model seems that it did not learn anything, which means that the first model, if we try to control for that particular concept, we can get an output that is somewhat reasonable. The second model looks like if we could try to control for that particular concept, we probably won't be able to. And that's what this plot shows here. So this is like we're trying to intervene on aromaticity for like our good model and for the bad model, and we can like successfully intervene for the model that learned that concept well, but for the model that the weights were basically zero, whatever we do for that concept, nothing happens because it's a linear layer that we multiply it with the activation. So increasing the concept activation doesn't really affect the output at all. And yeah, so this is a mechanism for debugging. And we can also always go in and change these weights to something we, like as humans, believe to be the right thing, if this is the case, and we can get a different output. So yeah, so this is kind of like everything I wanted to talk about today. So just to recap, our concept bottleneck protein language model offers control, interpretability, and debugging. The whole architecture is kind of new. We applied it to proteins as a start because we thought it might be very useful because we always need to control proteins and understand what the model is doing. So I'm happy to take questions Um, yes.
Yeah, we have one more question in the chat box.
Okay.
Most of the BioPython concepts are numbers which can be calculated exactly like hydrophobics using like given scale
Mhm,
for a given sequence. And
mhm.
for a given data set, these could be calculated and uses as features. What is the advantages to holding out the exact calculation number and asking the model to learn as a concept? Perhaps there are the convolutions or association benefits when some of the concepts are not easily calculable.
Yeah, so we added these concepts because they're a way to kind of verify that our model is doing the right thing, in the sense that if it's able like as like a sanity check. So we're able to calculate them in silico. So if we kind of make the model learn them, will it be able to change them? And then we can like just run it. But there are like you can think about it can be any concept. It doesn't have to be these in particular. So we have concepts that are not like Python concepts. You can think about like if you have a training data set that has affinity in it, you can add that as a concept. So these were basically first Python concepts are in fact somewhat useful. A lot of times people want to basically, for example, you can have an antibody that has a hydrophobic patch and you want to decrease it. So having these concepts were actually useful for production, but also they're very easy to test in silico to make sure that the model is doing what we expect it to do. But more complicated concepts can be encoded in this model, and you would need to basically productionize the model or test the output in the lab to make sure that that's the case. And like we kind of verified that a little bit in like some and some wet lab tests that it looks like the model seemed to be doing what we think it was.
Another question in here is, do you have intuition as to how you might implement CB-pLM if the concepts are calculable? Will you have to implement it in the training, like in a pair-based manner? I guess he's referring the DPOs.
Um, I'm not sure I quite understand the
Oh,
question.
the question is, how do you implement your model if the concepts aren't like calculable? If I guess like it's like when you train your model on the 700 concept you already have, when you have like a new concept, how do you train the model? You like just fine tuning and add another linear layer or somehow?
So one thing you could do is that you can have like you can have extra space in the model that you don't really assign concepts to. And then what you could do is that you fix everything and then try to put when you have a new training data set, you freeze the whole model and just try to learn the new concepts. You can also use like the unknown part to kind of like encode the concepts in them for that particular layer. So these are the two options. But yeah, you would need to freeze the weights and make the model learn the new concept, and then similar to like how they would like fine tune or like for example, when people do regular English language model and you have like new tokens that they didn't see in the training data set, you would have to add the token in the tokenizer and then kind of like train the whole model again while freezing everything else. So you would do something very similar. We didn't test that, but that's kind of like how you would do it.
Yeah. Yeah, I guess the next question, the questionnaire, should how ask how many affinity data would be needed to like train them on, retrain them on, or fine tune them on.
So it's really hard to tell. But generally speaking, like just from thinking about general language model in general, the fine-tuning data sets are pretty small in comparison to the pre-training corpus. So the answer is I don't really know exactly how many training data sets. It depends on like how also affinity. Um, is like one of those concepts that you need to have a very diverse training data set. So if you have like you have to have it for multiple targets, and so if it's well diverse, then you probably can train something that is reasonable. But if it's like on one target, maybe you won't be able to get any that much affinity when you like look into different targets. So yeah, it's hard to sell, but generally it's a lot less than what you need to train this backbone model. And just, yeah, fine tuning will probably work if you have a reasonable training data set. And it will probably work better than if you just took that fine tuning data set and trained something from scratch. And that's like kind of what we found in like like smaller experiments. So
Just out of curiosity, have you tried to like fine tune this on like real wet lab experimental data? Yeah.
So we produced, yeah, so we tried to like generate protein sequence and see if we didn't, for particular properties, we found that like for like affinity, so we started like from some sort of affinity and made sure like, okay, the new protein we designed didn't like break the affinity. The properties, some properties, it felt like it's actually doing what it wanted to do and it's improving. Like, or we think it's going to like improve the property that we have in like through the measurements that we found in the lab. So it looks like it's, yeah, doing the right thing.
Oh, okay. Thank you. Yeah, I guess that's all the question. And thank you for giving us the talk, and wish you
Thank you
have
so much
a
for having me. Thank you.
thank you. I guess that's it. Bye everyone.
Goodbye.